Hello, my name is Mr. Wilke, and today we're going to learn about inference for regression. So, as you remember, our least squares line is y hat equals a plus bx, where a is the intercept, b is the slope. Now, this changes as our data changes, right? Does that make sense? Good, okay. So, as our data changes, our least squares line will change. So, well, we can do inference about the regression line. So let's talk about the conditions. Now, whenever we do inference, step 2 is always conditions, so let's talk about what conditions need to be true. All right, we have in observations on explanatory variable x and response variable y. Now, you remember, how do we know which one's explanatory, which one's response? Explanatory is x because there's an x in it. Response is y because there's no x in it. That's right, good. Okay, so we have in observations on explanatory variable x, response variable y. We want to predict the behavior of y for given values of x. Okay? So let's talk about conditions, what we need to have be true in order to do inference. So for any fixed x, y varies according, get rid of that, to a normal distribution. Now, how do we know that? What does that even look like? So, let's say that's our least squares line. So for every x, should be a lot in here, so each x is going to have a normal distribution there. Does that make sense? Okay, good. So for every x, any fixed x, y varies according to a normal distribution. And repeated y's will be independent. Okay? The mean response mu sub y has a straight line relationship with x. Can you see that? Okay. So mu of y equals alpha plus beta x. So, wait, y alpha and beta, not a and b. Good, that's exactly right. It's a population regression line, so instead of using a and b, we use population intercept alpha, population slope beta. Good. Okay. So alpha and beta are unknown. All right. One more put this up here a little bit. There we go. So you can see. So standard deviation of y which is sigma, is the same for all x, and sigma is unknown. So what that means is each of these distributions here, remember it's normal for every x, well the standard deviation here is always the same. So basically what that means is for each x it's going to have the same size difference, right? The difference from the line is going to be, the average distance to the line for each x is going to be the same. So all of these distributions are going to have the same width. Does that make sense? Cool. Okay, let's pause, get that down. If you need to pause it, because, well, we're going to do some magic and erase it. And here we go. And look at that. Ooh, what's this? Oh, so to recap our conditions. Y is normal for all x. Repeated y's are independent. The mean of y is alpha plus beta x, which means we've got a straight line relationship. And sigma y is the same for all x. We understand all those? Let's hope. Okay. So, to do inference, we must first estimate alpha, beta, and sigma. So what's a good estimate for alpha and beta? A and B, that's correct, good. So the first thing we're going to do is calculate the least squares regression line, y hat equals a plus bx. All right? B is a good unbiased estimator of beta. A, unbiased estimator of alpha. To calculate sigma, or to estimate sigma, we're going to use residuals. All right, so does anyone remember what residuals are? Okay, that's correct. A residual plot was used to tell if the line was normal, right? Or to tell if the line was a good linear fit. Not normal, good linear fit. So if there was no pattern in the residual plot, we knew, okay, good, it's a good linear fit. But the residuals were the observed minus the predicted or y minus y hat. So if we were looking at the line, the dots are y, the point on the line is y hat, so it's the distance above or below the least squares regression line. All right, so the standard error about the line is this. So let's look at that. The square root of 1 over n minus 2 times the sum of each y minus y hat squared. Okay, so would that make s squared a variance? That's right, yes it would. How come? Because it's an average of squared deviations, right? So if we're averaging squared deviations, there we go. what's up with the n minus 2? Clearly it's going to have something to do with degrees of freedom, that's correct. So we have n minus 2 degrees of freedom since we have 2 variables instead of 1. So since two variables we have n minus 2 degrees of freedom. So let's talk about how to calculate S. Well, what do you think we're going to do? We need to know y hat, right? So to calculate S, L1 bx, L2 by, L3 will be L2 minus y1 at L1. Does anyone remember? That's right, it's the residuals. Good. Yes, so we're going to put x and y in L1 and L2. Stat calc 8 will give us our least squares line in L3, L2 minus y1 at L1. Okay? Now, can anybody tell me what the sum of L3 would be? Yeah, that's right, 0. Good job, yeah. Remember, the sum of the residuals is always 0 because you've got the same amount above the line as you do below the line. All right, so if we run one of our stats, stat calc 1, on L3, we get the sum of you can't read that because of where I'm writing it. Put this up here. I'm going to rewrite this for you. Sum of the squares, right? So if you look at your one variable stats, find sum of x squared. We ran one variable stats on L3. That'll give us this, right? Just divide it by n minus 2, square root it, and you've got S. Okay? Good? Everybody's got this down? Pause real quick. So we're going to erase everything. And erased. What do you know? Magic. All right, so we've got our conditions. We've got how to estimate alpha, beta, sigma. So let's talk about a confidence interval. Now, what do you think we're going to be doing a confidence interval for? Well, for y, that's right, for the slope. Good. Confidence interval for slope beta. All right, here remembers the formula for confidence interval. It's always statistic plus or minus critical value times standard deviation of statistic. So what's the statistic we're using to estimate beta? B, good. Plus or minus, what do you think? Z star or T star? Well, do we know sigma? No, we had to estimate sigma with S, right? So if we're estimating sigma, it's going to be T star. Now, S was the standard error of the line. We need the standard error of the slope, okay? So let's talk about what the standard error of the slope is. Standard error of the slope is S, standard error of the line, over square root of the sum x minus x bar squared. Okay? Now this is where upper 1 minus c over 2 critical value from the t distribution with how many degrees of freedom? That's right, n minus 2. Okay, now, if we're going to test the hypothesis, so let's think about this one. If we're testing the hypothesis of no linear relationship, well, what's B if, or beta, if there's no linear relationship? The slope would be 0, right? So H naught beta equals 0. This means excuse me. This means as x changes, y doesn't. Okay, so H naught says straight line dependence on x is of no value for predicting y. Okay? So to test H naught, we're going to find our t statistic. Remember the formula? Standardized test statistic equals what? Statistic minus parameter over standard deviation of statistic. Well, statistic is B minus what? Minus beta, but beta is 0, so we just leave it as B over SEB. Okay? So that's it. And find the p-value. All right, so I'm going to give you your assignment, or we could just do one. You want to do one? All right, so if you have your book, which is the Practice Statistics, I think version 2, because we've had these books for a very long time. New books next year. So let's get out your book and let's do 14.2. So I'll give you a second to get your book out, and I'll get my book out, and we'll go over that one. All right, so let's look at 14.2, which says Sarah's growth. Sarah's growth from age 3 years to 5 years was measured as follows. So there's age in months, there's height, I'm assuming in centimeters. Otherwise she'd be a really tall kid, right? Okay, so these data were entered into a statistics package, and least squares regression of height on age was requested. Here are the results. So we've got predictor, constant, coefficient, standard deviation, t ratio, p, constant, h. So constant is going to be for A, age is going to be for B. Does that make sense? The coefficient for B, right? So the constant is, so the least squares line would be 71.95 plus 0.38333x. All right, this is the standard deviation of A, standard deviation of B. T, p-value. See what we're going to do, right? Okay, so over here, I've got the least squares line. Now, what are we trying to show? We clearly have a p-value of 0. Well, let's see what the book asks first, and then we'll talk about everything else. So part A says, what is the equation of the least squares line? Look for the column coefficient. What is the intercept? What is the slope? Well, there you go. Intercept, slope. So the least squares line would be y hat equals 71.950 plus 0.38333x. Good? Okay. Part B, the model for regression inference has 3 parameters, which we call alpha, beta, and sigma. Can you determine the estimates for alpha and beta from the computer printout? What are they? Well, the estimate for alpha is A. The estimate for beta is B. Well, that was easy. Part C, the computer output reports that S equals 0.3873. This is an estimate of the parameter sigma. Use the formula for S to verify the computer's value of S. So, do we remember the formula for S? If you don't remember the formula for S equals square root 1 over n minus 2 times the sum of the squares of the residuals. So, what I did was I put all those in. I put the least squares line in. So now, how do we find the residuals? Residuals, L3 was supposed to be what? Y minus y hat. Y is L2. Y hat is Y1 at L1. So let's put in L2 minus Y1 at L1. Now remember, you have to already have your least squares line saved in your Y1. I did that already, so make sure you do that. So there's my residuals. So one variable stats on L3. Sum is 0, right? Sum of the squares is 0.6. So we've got 1 over n minus 2 times, well, what's n? 1, 2, 3, 4, 5, 6. So 1 over 4 times 0.6 and square root that. So let's just go 0.6 divided by 4, and we will square root the answer and hope we get 0.3873, and look at that, we do. I didn't try this out before because you can tell. 0.3873 is correct, so S, we got that. Now, what if the problem had asked us to do 4-step inference? Could we have done that? First, what are we trying to figure out? We're trying to figure out, well, the p-value, which we already know, but let's think some more. Step 1 would be, we want to know what? If Sarah's age is a good predictor of height, we want to know, is there a linear relationship between her age and her height from the time she was 3 to 5 years old? Well, H naught would be beta equals 0. HA would be beta is not equal 0, or are we assuming it's, we're assuming it's positive, right? It does make sense that age is a good predictor of height, right? As you get the older you get taller, at least from age 3 to 5, maybe a little bit more. Okay, so that makes sense, right? So beta, we could say beta is greater than 0. We could say beta is not equal to 0 if we don't know, right? Either way. Step 2, conditions. Now, here's the nice thing about this chapter. Is just about every inference problem I have ever seen with it, it always says, assume the conditions for inference are met. So in step 2, you would write, we're given the conditions for inference are met. Proceed with a linear regression t-test. Step 3, be over SEB, which is that, which gives us a p-value of 0. The printout did it for us. Step 4, since our p-value is approximately 0, we reject H0 in favor of HA. There is strong evidence to show that there is a linear relationship between that, or the slope is greater than 0. And that's it. Does anybody have any questions? Good? All right, well, thanks for coming. I hope this helped.